Hello everyone, this is another cheapo project. If you watched some of my previous videos, you'll have noticed you'll have seen that I did a really cheapo, very basic curve tracer, and I plan to do something similar, but this time it's a Kelvin probe. You can buy meters that measure resistance using the Kelvin bridge to measure low voltages. This is more of an add-on to a multimeter you already have. So if you've got a multimeter, especially a digital one, you just need to add this to that meter, and you've got you'll have a meter that can measure very low resistance. And I thought, and if you've seen my last videos, I did some showed you how to do some drawings for KiCad, because I wanted some test probes that I couldn't find, like these, and I showed you how to put them into KiCad. So I drew these. They look really great in this thing. They look just like the probes I'm going to use. I've even drawn a battery holder, because I'm going to run this on 3 volts. I haven't finished this circuit, the PCB, yet, because I'm still waiting for a switch. There's a switch that I need to draw, and I haven't got it, so I don't know what size or dimensions it is. So I've still got that to do. Let me know if you want me to see me draw a switch as well. This is a circuit. There's my 3. I haven't got my hand, have I? Hold on. Yeah. Here's the battery. It's 3 volts. Because what I intend to do is I intend to move on from this rather than use a multimeter with it. I'm going to make it as a standalone thing so that it works on its own, and for that I'm going to use the ESP8266 and the DAC I used in my curve tracer. And I'm going to take the measurements and do a display just like I did the curve tracer, but we'll be using this circuit instead. Basically this circuit, well, I tell you what, I think the best way to understand this is for me to explain how a digital multimeter works first, and then you'll understand the need for this circuit to add on to the digital multimeter, and to be able to measure low resistors. So I thought this time also I would write a script, well, some sort of script. So I've written something out to help me remember what the hell I'm talking about. And so my introduction is, in this video I'm going to show you how multimeters really measure resistance and current, and of course voltage, because basically that's all a multimeter does, is measure voltage. It doesn't measure anything else. And I know you're going to say, well, it measures resistance, it measures current, but it doesn't. It calculates those. It only measures voltage, and I'll explain how it derives at the resistance and current by measuring a voltage. All it does is measures a potential difference between 2 points in a circuit. That's all a meter can do. We can't measure resistance, and we can't measure current. We calculate them from other known parameters. And I'm also and why they struggle with very low resistances. This is the key thing. Using a multimeter to measure low resistances is a problem, and it's because of how multimeters are made and used. Let me just ask a question. you might want to answer, because I'm sure there's people know this, why we can't use a multimeter. So the question is, why can't we use a normal multimeter to measure low resistance? Is it because of the leads? Is it because no, I didn't write this down. Yeah, is it because of the resistance of the leads, or is it because of the meter itself, or is it a mixture of both? So yeah, there's like A, B, C. Oh, let's have D, none of the above. Yeah, tell me in comments if you want. Right, so because maybe some people may be wrong. Right, so that's giving you a hint, a big hint. Anyways, let's carry on. How a multimeter measures voltage. Right, so basically that's all a meter does. Basically, if you can imagine the old multimeters that had a dial, basically that was a coil of wire sat inside some magnets. So if you put some voltage through, it created a magnetic field and rotated the dial. It's the same way we measure voltage anyways. But we just now have something that displays it in a digital format on a screen. So it doesn't use anything else, it just measures, simply measures the potential difference between the probes. I've got a drawing somewhere, let me just get a drawing. Yeah, measuring volts. V equals V across the probes. So basically what a multimeter does is this. That's the only thing it can do. It can't do anything else. It can't measure current, it can't measure resistance, it can only measure voltage. And so you've got a big knob on front of your meter. Let's have a look. There we go, this big knob on front of your meter. And basically this is like a big multi-pole switch, and it switches things around. So yeah, and the terminals for this probe, this multi-pole switch, shall I say, it's got very thin bits of wire as the for the poles for the switch. They're very thin and lightweight switches, because all they're doing is switching very low current. The reason I'm saying that is because I want to actually tell you why we have the extra 10 amp connection here, and why you've got to actually swap a lead to use the 10 amp DC current. Yes, I'll come to that. Yeah, so right, where was I? I forget. Let's get back to my script so I know what I'm talking about. Yes, so that's all it does, and that's my picture. Where's my picture gone? There's my picture. So the voltmeter just measures from the probe, the common probe, and the normal probe. Let's just put that like that. And so that's my black one there, and then this is my blue one, and call this my red one. So you can see that it just measures the voltage from this probe and that probe. Yes, so let's move on. How does it measure current then? Well, this involves the usual thing, Ohm's Law, V equals Ri, and we just shuffle them numbers around to get what we want. So a multimeter measures current when you switch the current mode. Now there's two modes on here. There's the 10 amp mode. Basically what this switching 10 amp mode is doing is disconnecting everything inside, basically. But in this milliamp mode, what it's doing is it's catching up this lead through a shunt, and I will show you that. Where's my thing? yes, like that. So when we turn this round to one of these, so it could be anywhere in this area, all we're doing is shifting a resistance, and we're measuring across a small shunt. So what we have inside this multimeter is a 1 ohm. So, well, it's probably a 1 ohm. I think that's what's in here is a 1 ohm shunt. So what we do is we pass the current through our normal, our if we do milliamps, the current runs in there and comes out here, or in there and out there, whichever you want, and it runs through this shunt, and the multimeter measures voltage. So what it does, it measures the voltage across this shunt, and we use Ohm's law to find out what the current is passing through this shunt. So like I say, a multimeter only measures volts. It doesn't do anything else. When you've got that this lever in this position, what it's doing is measuring the voltage across this shunt, and we know what this resistance is. It's 1 ohm. So it reads the voltage. We know this is 1 ohm. And so we divide the voltage by 1 ohm and we get the ampage coming out. So we're still only measuring voltage. And obviously we've also got this one down here, like that, for the 10 amp. And what that does, you switch, it disconnects well, it sort of isolates this because we're running 10 ohms through it, but it still measures. So if we go like this, no, not that, we're measuring the 10 ohms. It's still the same formula. We still measure across this shunt here. I've put the shunt on this side here so it was easy to draw. But now we're passing the current through here, but this is a different shunt. Can you see I've put there 0.01? And if we look at inside the multimeter, we can see that we've got this big lump of wire, and that's the 10 amp one. And the reason we have to switch to this to this socket is because we don't want 10 amps running through this switch. This has only got some little thin plates as connectors inside here. The connectors inside this rotary switch that we move around won't actually handle 10 amps. So all this switch is doing is moving the connection of this voltmeter here. So this voltmeter is moving these connections here to this big heavy shunt here, and so the 10 amps is actually coming in on the negative here. So that's our negative. It's hitting that shunt there, it's going through that big thick wire here, and it's coming back out here through that red one. So there's my black lead coming in here, goes through that big thick shunt which can handle the 10 amps, and then it goes straight out that socket, which is that one there. So we haven't got any 10 amps actually running inside this circuitry and through this switch on the front. All the 10 amps is actually running from there through that big thick wire, the shunt, and back out again. This switch on the front, all that does is just measure the voltage between them 2 points there, which it's doing there. You can see that there on there. So that's all the switch does, is just connects the voltmeter, our meter that measures volts, across either end of there, and we can measure the potential difference across there. And this is a very low resistance. And on a side note, let me just get my microscope out because I want to show you something. Right, here's my microscope, and what we're going to look at is this thick bar. I don't know if you can actually see on this that this bar is made different to this circuit board there. The two circuit boards are actually soldered together with solder joints. Let's just focus in on that. There, can you see that this is like a separate board? Because this is made different, because this wire, this shunt here, has to be very precisely calibrated, and I think what they do is they make this board first. Well, they make the two boards separate, and they come together later on. But I want to show you how they calibrate this shunt here. May be of interest to some. Let me just bring back my microscope. Yeah, there's my microscope. Let's focus on oh, hang on, let's just get it focused there. Yeah, or maybe just tip it up slightly. How's that? Get it right in a minute. Give me a minute. It's not playing the game, is it? Anyway, I'm going to get my microscope. So, here's my microscope, and if we look closely at this bar, let me just get it in. Focus. There we go. Don't know if you can see, but it's got some little nicks in the copper wire. Where are we? There. Let's just try and get a side view. There, can you see that nick? There, and you can see that nick there. These are done with like a pair of tweezers. They're just, imagine just putting a little nick in a bit of wire, and that's how they're calibrated. What they do is they just put a nick in, and it changes the resistance of that wire, and that's how close of a tolerance this wire needs to be. You put a nick in, and it changes the flow of the current and the resistance, so you get a thinner bit of wire and the resistance drops, or goes up, shall I say. Yeah, there's more resistance because it's a thinner wire gives you more resistance, and that's how they calibrate them. I just thought I'd show you that, just as a side note. If you ever want to look inside your multimeter and you look at the bar and you think, well, what's them little nicks in it for? And that's actually calibrating that length of wire to be very accurate to a low resistance. Like I say, on that wire, where's my picture? On that wire, it's because we've got 10 amps going, could have 10 amps going through that shunt. Our resistance wants to be as low as possible. If it was a high resistance, it would get hot, wouldn't it? So and it would alter your reading at 10 amps. That might give you a clue as to why we need an add-on to measure low currents. Low resistance. Get it right? Yeah, I'm giving it away now. I'm giving game away. Yeah, that's why we need that's why we need an external device to measure low resistances. Yes, there we go. Right, so where's my notes? I can get rid of that now. I don't need that magnifying glass. I can drop that down. We don't need that anymore either. We all know what a general. Oh yes, actually I didn't show you this. Yes, before I forget. Right, so I showed you this shunt here for the big resistance, and it's a very low resistance. and we calibrate with things. But when we're doing it in this mode, right, this mode, we're plugged into this one, which means we're actually going through the contacts on this switch, because we've only got a low, we've got milliamps, microamps. So the switch here can handle milliamps and microamps. It can, and so we can use the actual pin, this socket here, because it can run through this switch. And what this switch does when we're in this mode, it runs it through a different shunt. See if I can get that in focus. So the 10 amps is going through this shunt, but there is actually another shunt there. I don't know if I can focus it in. Can you see that's 1 ohm? 1 ROO. Let me turn it round. There we go. Oh, get the glare out. Yeah, so there's the big one for the 10 amp. And here, can you see these three here? These are the shunts. Let's get in focus. Come on. These are the shunts with that one. I can't read them. Should have left my microscope on, shouldn't I? But these are the shunts for. Let's get that focus in. For these ranges here. So that's for these ranges. You say, well, there's 4 ranges there, yeah, but you add two resistors together and so on, basically. Use all 3. 2 or 1, I think. Anyway, it's a mixture of those resistors that it uses depending on which position you have this switch in. So this switch, what it's doing is actually switching these resistors. It's either using 1, or it's using 2, or it may be using these 2, or maybe using all 3, depending on what position you have it in, and that gives you different values here. And I can read that one is 1 ohm, that one. But for the 10 amp, it has to go through this big, heavy one that can handle 10 amps. Right, there we go, got that out of the way. So let's continue with me script. So we know we're on, I keep repeating, we can only measure voltage. So we've got our picture there. Where's my script gone? Yes. So it inserts a shunt. So when we switch to current mode, basically the meter changes internally. It inserts a shunt resistor in series with the circuit. All the current flows through that shunt. The meter measures the voltage across the shunt, and it calculates the current using Ohm's Law, I equals VR. So there we can see that. So like I say, the 10 amp has to go through a big 10 amp shunt, and the small milliamps can go through one of those little tiny resistors that we had. But basically, whichever shunt we choose, that's what we're measuring the potential difference between. So like I say, we can only use these small resistors internal on that big dial when we're using these small resistors here on the milliamps. That's a key thing, that milliamps. Right, so let's continue. I'm a very bad explaining things, I'm sorry guys, but so even in current mode, the meter is still just measuring our voltage across its own shunt. That's another clue. Own shunt. Right. Yes. I keep repeating these things. It's mainly to remind myself what I'm actually talking about. different probe sockets route the current through a different shunts, like so. We've got milliamps, 10 amps, etc., which I just tried to explain. Yeah. So we come to how this is the important bit now, is how a multimeter measures resistance. Like I say, a multimeter cannot measure resistance directly. It can only measure voltage. That, you know, we've got there's no ohm sensor inside it. It has to measure voltage again. So what it does, it generates a small known current. Let me get the picture. Right, so we're not using a shunt now. When we switch this big knob on the front of the multimeter, it switches things around and it turns on this current generator. It generates a fixed current. We know what this current is. It's a fixed current, and we've decided what that current is. It's known. And we measure the voltage across these two probes. And the resistance, see, we're not using the shunt. What is actually the shunt is the device under test. We're actually measuring a resistor here. If we put a shunt here, that's what we're measuring across the shunt. We're measuring across the device under test that we're actually putting a fixed current into. This is only a small current, it's milliamps, because remember, this switch can only handle milliamps. It can't handle amps. Only milliamps, because it's got tiny little tabs inside, if you've ever stripped one apart. So yes, so we're still using the formula, Ohm's law. So it sends a current through the unknown resistor. The unknown resistor being this device under test. So we're sticking a resistor on these two probes to find out its resistance. So it sends a current through that resistor, unknown resistor, because that's what we want to find out. It measures a voltage across that resistor, like it did before across this shunt, but now that is the shunt, the resistor. And it calculates the resistance using R equals VI. Well, we know the voltage because we've just measured the voltage, and we know the current because we've set that current to a current we know. This is a fixed current, and it's a known current. So we know that, so we can calculate the resistance across here, and that's how it measures resistance. It does it by measuring voltage, and we generate a current. So yes, I think that explains that. Voltage measurement plus calculation. It's important later. So why multimeters struggle with low resistance? So let's say now that we want to measure with our thing. Let's put, where's resistance on there? Resistance. Yeah. We can go down, say we went down into this range here, 200 ohms. This is 0 to 200 ohms, but we'll find that once we go below 1 ohm, in fact, probably below 10 ohms. Once we go below 10 ohms, that the reading that we're going to get out of here is pretty much guesswork. It's not very accurate when we're in this position, and the reason being, the current in a multimeter used in resistance mode is very tiny, often a few milliamps or even microamps, and for every small resistor like 0.1 ohm, a tiny current times tiny resistance gives tiny voltage. The voltage is so small the meter can't resolve it accurately. That is why we can't measure small resistors. So the answer to my original question, is it the leads or is it the meter? It's actually the meter that can't measure, because the resistance is so small. People think it's the leads. Well, it is sort of the leads, but it's mainly the actual meter. The current it generates to measure and do this formula, this current generator, is very small, and it's so small when we measure the voltage across a low resistance, a low resistor across here, the voltage measurement is tiny. It's in the really tiny millivolts. It can't. Well, like I say, I've said it there. It's small. And the contact resistance, well, obviously we've got the leads, they are involved. The contact resistance swamps the readings. So it's not just the leads, it's the actual meter itself. It doesn't produce a large enough current so that we can actually measure a low value resistance. And do you remember me telling you that to do a when you do the 10 amp measurement here, we're using the same formula, but can you see that we have 10 amps here, and this shunt was only like 0.001, and so the ratio between the resistance and the current, the ampage, was good enough for us actually to measure the current flowing through. So we need to do something very similar. We need to increase the current. That we have to produce a larger current than this meter actually can produce to measure the small resistance of small resistors. So while we need yeah, right. So this is my adapter. This is this piece. Where are we? This is this thing, and what this is, it's a fixed current generator. What this circuit does, I can switch between two ranges. One is for 1 ohm resistors, and one is for 10 ohm resistors. Well, this is for measuring 0 to 10, which isn't as accurate as measuring 0 to 1. So this will give us a value 10% more accurate than this one. So I can switch between the two different currents that we actually feed through the resistor under test. And then what we do is we measure the voltage across here with our meter. So what we're doing with this is we're moving this outside of the meter. We're making a new one of these, but with a greater current. And with a greater current we can then just use this mode. So we set our meter into millivolts. We set our meter here, and we measure, where are we, voltage, that's DC. We set it into the 200 milliamp range. Well, actually I'm not going to use that, I'm going to use my other one. Hang about. I'm going to use my digital meter. Right, so forget that, twiddling that now. Let's go back to here. Yeah, so we set our meter to measure just volts. This is what our meter does, and then instead of using this internal generated current, what we do is we generate a current externally on these two pins using this circuit. Yeah, let's move that over there now. Yeah, so what this circuit is this bit here, how I used to have it before. Oh, it's that one there. Right, so you can see the current is generated there, and we've got this current attached to this probe, and we've got it attached to that probe. So what we do is we put our meter just to measure voltage. We're not going to use that anymore. We're going to attach this to this probe and that probe, which is the same position as the test point that we're going to put our resistors. We put our resistor across here, and we also put them two probes across here. That gives us our resistor, which is this shunt, and this circuit here gives us our current generator. Well, I hope that followed it. Anyway, where's my notes? Let's have a look. See what I wrote down, because it helps. Yeah, so yeah, to measure a low resistance accurately, we need a larger, scalable, predictable current. So that's what this circuit does. This circuit gives us a larger, predictable current. When I say predictable, I mean at a set current. And a clean measurable voltage across the device under test, which is obviously our meter, is just measuring voltage now. Yeah, that's it. Oh, there. A way to keep the multimeter reading what it does best, measuring voltage. So the adapter simply moves the current source outside the multimeter, and the meter goes back to being a pure voltmeter. Yeah, there we go. How does the adapter work? The adapter generates a constant current. It uses a... oh, where's my circuit? Oh, gone. There we go. Let's move that down. It uses a transistor. I've got this transistor here. Let's just bring that down. There we go. Yeah, it uses a transistor there. It uses the diode reference. So this diode here, we've got, these have a forward voltage of say 0.6. So we've got like 1.2 with them two diodes. That gives us our reference, and we've got a resistor, so we're not actually shorting everything out. This acts as a load, and we have our calibrate sense resistor range down here. So we don't actually need these two resistors. We've got these variable resistors, but in practice you should always put a resistor in there in series, so that this potentiometer can't go lower than a certain resistance. Otherwise, if this wasn't here, basically when this was trimmed down to 0, you're effectively putting a short in there. So you need something to stop you actually creating a short, so that this potentiometer, so that the total resistance down here can only be as low as 10 ohms, and this one can only be as low as 1 ohm. We could have just put 1 ohm in each one, like, it doesn't really matter. But since this is like 10 times higher than this side, I've put a 10 ohm resistor in there, but it prevents you from actually rotating a potentiometer down to 0, because if you add one, so this can, well, I'm sure you understand what I mean. Where are we? Yeah, and then I've got a range switch. So this is this switch. This is what I'm still waiting to get and draw in my circuit. So we can either have 0 to 10 ohms, and or 1 to 10 ohms. Sorry, yeah, or 0 to 1 ohm. So the way I've calculated this is, when we're on this side, on this 1 ohm resistance, the voltage across these 2 points are going to be 100 milliamps. So if we read 100 milliamps, it's going to equal 1 ohm. So to make it easy to divide in your head, the calculation, you just divide the reading on the meter 100 milliamps divided by 100, and you get 100. You get 1 ohm. And this side, I've designed it so that 10 ohms equals 200 milliamps. 10 ohms equals 100 milliamps. So if we get a reading of 100 milliamps and we divide it by 10, then we get 10 ohms. Yeah, right. So hopefully that was clear. Yeah, so like I was saying, the device under test becomes the only resistor in the circuit path, which is like having that shunting when we were measuring before. The multimeter measures the voltage across the device under test. Because the current is fixed, the voltage directly represents resistance, and we actually calibrate to make sure that the 10 ohm resistor when it's on this circuit measures 200 milliohms. We have this variable, this potentiometer that we can preset using a 10 ohm, a known good 10 ohm resistor across the device under test. We calibrate it by adjusting this, and then we can go to measure other stuff. So yeah, I added at 200, but that meant dividing it like half, divide by 10, well, divide by 5, but divide by 10 or 100, maths were simpler. So it's basically, so yeah, that's what I was saying there. 1 ohm equals 100 milliamp, 0.1 ohm equals 10 milliamp, 0.01 ohm equals 1 millivolt. So you can see that we can measure down to 0.01 ohms and we get 1 millivolt. Or if we want to, in the 10 ohm range, we can get 0.01 of an ohm equals 1 millivolt. So this is like a coarser measurement, and this is a finer measurement here. If this went down to 0.1 millivolt, so it was like 0.01 millivolt, then it would be 0.001 millivolt. So this can get very accurate. I'm going to show you in a minute. Let's see what I've done. Yeah, so in summary, a multimeter always measures voltage. Current mode uses a shunt. Resistance mode uses a known current. Low resistance needs a bigger stable current. It's not just because we've got long leads and it adds resistance in the circuit. That is a factor, but to be able to read the voltage across the lower resistance, we need a larger voltage. A larger current. We need a larger current so we can actually measure more accurately the voltage across the potential difference across the resistor. And that's what my adapter does. It provides that the current externally, and the meter reads the voltage and gives accurate milliohm readings with any multimeter. So you can add this thing to any multimeter. You can add it to an analog one if you want, but you've got to be good at reading an analog meter. I think that's it. Yeah, that's it. So let's just have a look. So at my circuit again. So I'm going to minimise that. So there's my circuit, and here it is on my bench. Right, ignore this because this is my next step. This is an analog to digital converter. It's a 12-bit analog to digital converter, so it's very accurate. And this is my ESP 8266. All I'm doing is using this linear regulator to get 3 volts out of it. Well, 3.3 volts. Well, I'm actually getting 3.1. And then this circuit, this resistor and these diodes put a constant 1.5 volts on there, which then gives this a constant current running through here, basically. Yeah, so ignore that and that. What we've got is got my resistor. There's my little resistor there. There's my two diodes. That's my two diodes. That's my little resistor here. That resistor. I haven't got that switch. That switch is this wire. this is oh right, yeah. I've got this turned on all the time, so I haven't got that switch in there. It's connected directly to the thing. It's this switch I'm on about. So this switch is this wire, this white wire, and what this does, I haven't got them two resistors in, but I've got these two pots. So what this white wire does, if I have it connected here, this is the 10 ohm one. Hang on, just rid of that. Get that out of the way. Yeah, just knock everything, including my camera. There we go. Yeah, this wire is acting. So if I plug it in here, I'm plugging it into the 10 ohm, and if I plug it in here, where are we? Plug it in here. I'm plugging it into. Oh, sorry, I'm plugging it into the 100 ohm there. And I'm plugging it into the 10 ohm one here. Yeah, watching me do that on camera. Yeah, so that's it. So yeah, there's the two pots there. There's the resistor, two diodes, and that other resistor. And my battery is this thing here. So let me just turn that on. So I put power into it. And what I've got here, let's zoom into these. Let's turn it right way up. So basically, these are all within 5%. Really, I should have really. You want some within 1% to calibrate, but I've already calibrated them two pots, and so these are 0.1 ohm each, so we've got 0.1 ohm, 0.1 ohm, and so it'll go. So as we go through here, it'll go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1 ohm. So we've got a total resistance of 1 ohm over the whole lot. So let's just connect it up. I'll get rid of that. So basically what this is here, let's get my hand. So what this here is a current source. It's a fixed current source is this. There we go. And that's what we're adding to the resistor. So if we put that on there, and that on there, that on there like that, what I'm actually doing is I'm put a current, running a fixed current through this resistor, and because we know the current that's going through this resistor, we can also measure the voltage. So what we're doing, let's get a picture, is we're creating a current. This current here is this bit. We're creating this current. I've got our device under test, which is this resistor, and what we're going to do is we're going to get my other meter. We're going to get this meter. Let me just turn it on to millivolts and turn on the Bluetooth and connect. There we go, we're on millivolts, auto DC, and what we will do These are my two terminals. These are to meet my two probes from my multimeter. Connect one to here and connect one to here. And can you see it says 9.9 millivolts. What have I got that plugged into? Can't see. Oh, I wonder if I've moved something. Oh, right, yes. So, yeah, I've got it into my where's my circuit? Yep, so let's just move my circuit over here. So what I've got it plugged into is this 10 ohm potentiometer, this one here, which is for my 1 ohm range. So we take our voltage reading and we divide by 100. So if we divide that by 100, we move our decimal point 2 places, 1, 2, and that gives us our 0.1019 millivolts. What this is actually saying is, give me a moment, I want something to draw on. Yeah, I just wanted something to write on. So what our reading here is, we've got 10.2 millivolts. So if we go 10.2 millivolts and we divide that by 100, that equals 0.10. Oh, well, it's 20 now, but anyway, yeah, oh yeah, 2 ohms. So we've got a very oh, hang on, well, yeah. So we've got a very accurate reading of the resistance. So what should happen is, this is on 10 millivolts. We go to here, we should get about 20 millivolts on the next one. So I'll just move that to the next. So I've moved the current source, so it's going through both them resistors. So the current source is on between, so we've got these two resistors linked together. So our current source is applying current, our fixed current, through these two resistors, and I'll just stick, we've still got our one end of our meter on the first one. It'd be best if I just untangle them. Best if I have that up there like that. There we go. So you can see them, and then I can put my red lead on here, measure the voltage across, and we can see now that we're reading 20.8. So if we do the same sort of calculation there, 20.82, yeah, let's go for that, and we divide that by 100, that equals 0.2082 ohms. There we go. How's that? So like I say, we're reading 0.2 of an ohm. I could go through all them if you want, all the way up to the end, but I think you get the picture. Every time I go across one of these, we're going to increase by 0.1 ohm. So what I'll do, what we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I like things simple. Let's put the current running through all 10 and measure the voltage across all 10. And there we go. What we have is 106.8, and if we divide that by 100, that equals 1.068. There, that's it. So that is pretty well, I've got some pretty accurate resistors there. They're a bit closer than 5%, I think. What we've got 6. Yeah, like I say, divide that by 10. They're pretty accurate resistors. So yeah, I hope you like that. Right. So what I was going to do, let me just move this in. Right. So this circuit, anybody can copy that. What I'll do is, once I've got my switch, what I will do is where's my thing gone? There. I will finish the PCB off, and if anybody wants this, once I've finished it, if anybody wants that, let me just get rid of that. If anybody wants this add-on, basically what you do is, these two terminals is where you're going to put the device under test, and you plug your two leads from your meter in. Or we can, what I'll do is I'll add two leads that go to your meter, and then you just plug your device under test here. I'll add a test. I'll add the, I haven't added the button, have I? I haven't done the button yet. Yeah. Where's the button? Oh, I haven't got that button on yet. Yeah. So I want this button and this switch on. So I'll have the test button, so you can just press it to test, and then you'll have this switch to do the range. And if anybody wants the Gerber files or anything for this PCB, where are we? For this, basically, I will do one. But what I am actually going to do, my next part, yeah, because this is only part 1, I am going to turn this, let's pull all that forward, I am going to add this and this. So this here will replace the actual meter. It'll replace my meter here, and what it will do, it will display a web page, or even an OLED, a little display with the actual ohms. So you don't have to do any actual calculating. It will just read what ohms that it'll display the actual resistor reading on the display or on the web page. So yeah, I tried to extend this a bit, so I'll give you a bit of a view. You don't have to, like I say, for this thing you're talking like what, £3 or £4 for the PCB and parts, instead of buying, if you've already got a multimeter. You don't need to buy one of them fancy Kelvin probes meters to measure low resistance, or a separate meter. You can use this as a plug-in add-on to your current meter or any meter you've got, and you can actually measure low resistance when you need to. So yeah, I hope you found it was interesting. I know I ramble on a bit. Oh look, I managed to get this one down to about an hour, I think. So yeah, oh that's good, at least it's only 1 hour now. Yeah, so I hope you find it finished, and what I'm going to do next is, once I've got my other parts, I'll do the PCB as I say, and anybody can use that, or you can wait for the second part where I'm going to introduce this digital to analog converter. So this will actually take a measurement of the voltage, and my ESP8266 will display it on a web page or on a small display. So it can be like a standalone thing. You just plug it into your USB 5 volts, and it runs on its own, and you can measure a low power thing. I mean, the whole thing, it must cost less. Well, I don't know how much did my curve tracer cost. Was it under £6 or something? Anyways, I hope you enjoyed it. I'll catch you on the next one.